Hi, my name is Dennis. Welcome to Foundations Networking, Ports and Protocols. Today we're going to learn more about identifying use cases for common protocols and services. We'll examine the payload and communication sequences of a typical TCP/IP stack. We'll understand what a stack means in a little bit. We'll also understand helper protocols that what layers that each service operates on. So helper protocols such as ICMP, different ARP, and different other messaging information that helps other protocols function and actually collaborate between different OSI layers in most cases. Let's get started. So first things first, layer 4 protocols. Right? Our main two are TCP and UDP. What do they stand for again? Transmission Control Protocol and UDP protocol. But first, what is a port versus a protocol? Now, some people get confused, and that's okay. Let's learn a little bit more here. Port is something that you go into. So think of garages. In different analogies for OSI model, you can think of a port as just a garage parking space 1, 2, or 3, but you don't know anything else other than, well, what about the address of the house that you're going to from point A to a point B? Now, you have that at IP version 4 header, which is a source or destination IP address, but the port is just saying, hey, I have a bay number. Park yourself here within this host or this client accordingly. So that we create a virtual socket or virtual connection. Right? Remember, they're just bays inside the actual TCP connection or UDP connection. Now, there are 2 to the 32nd, or actually 2 to the 16-bit addresses, so they're 2 to the 16. And so really, you have up to 65,535, and you can have very high ports listening and sending and receiving accordingly. The protocols themselves, TCP and UDP, are the protocols that they transport over. So what does that mean? Well, you could have carriers such as UPS, or you could have USPS or FedEx. Those are all different carriers, and so just because you have a different way of the data may stay the same, but you may have a different way that you need them to send. That is a protocol as opposed to a port. Your mail carrier of FedEx, for instance, will not send to a known PO box. Right? That's only a USPS. Right? That's something that goes there. But your PO box number or your residential number for your garage or other information where they're going to send your package is your port. That's your port number. So remember, ports are just virtual doors. Right? Any protocol can operate on any port. So typically, you might have seen TCP operate on 22, port 22 for SSH. Well, can it operate on 64,000 or 65,000 something? Sure. Right? It's just a garage space. We're not actually transporting the actual protocol, which is a defined set of rules that must be followed based on software specification. That's the main difference. So remember, port is just where you throw something at. Protocol is how you need to throw it at it, right? How you need to throw the data from one area to another. That's as simple as it can get. Remember that protocols are focused around behavior. Okay, so let's look at TCP connections in a little bit more depth. We have what's called a three-way handshake, and TCP connections are stateful. In fact, there is another one called a four-way handshake, in which that there's instead of a SYN ACK coming there, there's a separate connection for the SYN and the ACK flags. But let's not focus on that. That's actually a very interesting edge use case there. One thing that we need to know is that what happens initially. When the client sends a SYN synchronization, that sets a TCP flag. Right? TCP header has a flag, and it uses the SYN item right here. In a typical three-way handshake, once that SYN is received based on an open port, right, the port has to be open. A synchronization and ACK acknowledgement flag is in there. Notice that the synchronization number is a unique number, right? It's some sort of 32-bit unique number, or actually a 16-bit unique number in this case. And then we have a sequence number that is created on the server side, which is different. But it does acknowledge for the next byte over, or the next acknowledgement number should be 101 versus 100. The final acknowledgement is sent back, completing the three-way handshake at sequence number 101, where it's going to send stuff, and then acknowledge the original sequence number of the server of 201. Now, if this looks confusing, you'll get plenty of practice with this. Just remember that everything goes into synchronization and acknowledgments, and they keep incrementing accordingly based on the byte numbers, right? What's the next byte expected? Now, it increments by 1 on the initial handshake, right? Because there's no actual data being sent in between. Now, there is a such thing as sending data with your initial send. That's called TCP fast, but we won't cover that here. The main thing is for TCP connections, you have a 3-way handshake. The final act is your completion. Let's go back here and get my original pin. There we go. Right here is when you finally create a session establishment based on the final act. So just know that increments of sequence numbers and acknowledgement numbers happen by 1 on the initial handshake. But when data is acknowledged each time, it increments based on the number of bytes on that data for each regular act after this. So to continue this, after this initial sequence number right here that creates that connection, it'll keep going like this for acknowledging bytes sent thereafter. So if you send 20 bytes here, right, this is going to acknowledge the last 20 bytes accordingly. Now these are terrible handwriting, so I'll make that a little bit cleaner. This will be a little bit more apparent to you as we go to our labs and information. So we'll have ACK, and so you might have a plus 20 here for bytes, right? So what's the order again? 1, creating a handshake, which is initiated by the client. 2, our synchronization and acknowledgement. And finally, 3, our final acknowledgement to the initial to the second send right here. All right, TCP support, right? You have other items here. Remember, they're also a supporting layer, supporting protocol, but not a true supporting protocol. They're just a layer 4 protocol that helps wrap and create the initial socket connection. Your payload or your data, if you're looking at a mail carrier, they don't understand what is in that package. They just need to deliver it from point A to point B. That's the layers 3 and layers 4, by the way. But layer 7, the application layer, really the payload's on you. So let's say I'm sending you a package or you're sending me a package, and I have an encrypted code or some sort of message. But the mail carrier is not going to go digging into that. It just needs to get to me reliably. All right. What I do with your message and what do we do back using snail mail, well, that's on us, right? We're the two applications, even though we're people. Same thing happens with TCP versus an actual layer 7 protocol. In my case, instance, I have Telnet here, which is an antiquated protocol that is not encrypted by default. And it allows me to log in and provide a shell, just like you have bash shell. That's at the application layer. TCP has no understanding of what username and password mean. It just needs to get a virtual socket. Hence, we have encapsulation delineated right here. There are many other application layer protocols based on the payload. Again, those are higher level protocols, usually encapsulating layer 7 related protocols. Aware of that. This creates an abstraction that you don't have to understand. Applications need to understand exactly how TCP works. It just needs to specify that it's going to go out via a TCP object or encapsulated packet. Now we talked about creating a TCP connection bring up. Now we need to talk about a TCP connection tear down. So there's what this is called a 4-way tear down, which we call a graceful clearing of the buffers, right? Graceful tear down. A fin is created to say I'm finished with sending you data, then creates an acknowledgement and also another finished on their synchronization side, followed by a final acknowledgement, and finally your connection is closed. There is a non-graceful way of stopping the connection on either side, and we'll get to that shortly. Just know that 3-way handshake is typical for creating connection. 4-way teardown is also a handshake for graceful connections. Now there's something called TCP interrupt, which is a non-graceful way of saying stop the connection now. Let's say I'm creating a send packet, but I don't want to actually go to that port anymore. I'm sorry, it was a mistake. I use TCP reset as a flag instead and saying stop the connection, and then both sides stop. Usually you get this when you use Control Z or Control C, abruptly ending your connection, such as when you use Netcat or other protocol based tool sets for that. The interesting thing about this is TCP resets, when they kill a connection, both sides are supposed to stop. But you can also actually spoof these packets and connections using programs like TCP kill, which you can download accordingly. Now, when you think about intrusion prevention systems, and if they're out of band or not in line of not actually physically killing the connection via um, a software application package, you can use resets instead, which hopefully kill one side of the connection. So you'll send spoofing that happens. The problem is you do have to spoof the synchronization as well as the acknowledgement segments on both sides, and they have to be correct. Really challenging items, but TCP kill can help you do that and halt the connection and process based on a combination of IP addresses and ports. Really cool stuff, but that's a great way to say stop connection now. Don't worry about no one else talk. And that's a great way for like emergency teardowns or things that need to be stopped immediately, such as malicious traffic. Now, we talked about encapsulation in previous modules, but remember that TCP has a header. Here's what the header looks like. We saw IPv4 headers, and this is one abstraction on top. The IPv4 has a TCP header encapsulated within the rest of the data segment. But as I said, we have 16-bit ports, which are source and destinations accordingly. That's 2 to the 16th, which means 65,535. And if you don't remember that number, that's okay. It just means that you'll get used to remembering that later on if you deal with more with networking. We also have sequence and acknowledgement numbers with our 32-bit ranges, so 2 to the 32nd. And of course, you have your flags. So if I have a send flag and an acknowledgement flag for my second part of my three-way handshake, those will be marked with 1 versus 0 bits at the bit level, not the byte level. Notice that we have bits and bytes and information right here according to the actual diagram that you see here. A quick tip to also note is that RFC 793 is actually the RFC number for TCP specification standard. What about UDP connections? So if TCP is stateful, which actually has a handshake and it has to acknowledge very specific data coming in and out, what about UDP? What kind of use cases are for them? Right? You have the unigram data protocol, and that basically says send data, I don't need a response. But all the data requests and responses need to be handled at the higher levels, which is the application layer. You see right here that UDP just basically says, I'm sending and receiving, has no mechanism for resending anything, or what happens if there's dropped packets. The application has to understand what to do with those. Now, it's considered unreliable, but it's less reliable than TCP. In fact, that it doesn't track it for you at a lower layer. That's what it really means. It's really built for speed. So for instance, if you notice call qualities go up and down over time, you can afford to miss or have a small delay if you're having one person talk at a time. That might be useful for voice over IP address information, DHCP, where you can afford to have packets drop and then the application will just resend it out. ARP might be okay with that as well, but ARP is at layer 2. Remember that UDP is at layer 4. So layer 7 will right on top of UDP for items that don't require an actual stateful connection. DNS, DHCP, Session Information Protocol, which establishes as part of a suite of protocols for voice over IP information. Simple Network Management Protocol, which allows you to potentially control or see health statistics based on IP addresses. Now, our UDP headers look a little bit more simple, and they're fixed at 8 bytes. Right? You have a source and destination port, which is, again, 16 bits wide, just like with TCP, and then our length and our checksum right after that. RFC 768 is the actual RFC number for the actual UDP compliance, and really this is send and forget. If you don't get the data, that's not my problem. Let the application handle it. It's not the network's problem at that point. So we're moving on to layer 7 common administrative protocols accordingly. So let's dig down and deeper into what that really means for us, and then how we can utilize helper protocols in tandem with lower level protocols like layer 3 and layer 4. All right, let's move forward here. SSH, or single secure shell, is actually not just a protocol, but an interesting fact or topic is that it was actually a company that created that. So if you go to ssh.com, you'll find that the company created this protocol. And the whole reason why you can actually log into Linux-based hosts from a distance. You have a client server, and it utilizes encryption always and enabled. The most common one is SSH version 2, which is the later edition. There were issues with SSH version 1 with man-in-the-middle spoofing from a security attack perspective. but it utilizes certificates for its actual encryption as well as sometimes authentication. So instead of having a password, you can have a certificate based on your authentication instead. And this is great for automation and other requirements such as automatic patching, automatic Internet of Things, and how to authenticate to different systems. Ultimately, it utilizes public key technology. So you have a private key that's a client that has that private key that never is shared. And the server has a public key, just like you would with SSL or TLS. Remember that SSH allows you to have logins, file transfers, and other tunnels. And because it's considered a tunnel-enabled protocol, you can actually use other applications against within an SSH tunnel. For instance, let's say you don't have a secure version of VNC, which is a remote desktop-based terminal. You can wrap it with an SSH using two Linux hosts instead, or Linux and Windows hosts that someone has to have the SSH listener. As long as they have a client, they can actually send the actual data through an encrypted tunnel. Otherwise, that wouldn't be supported natively out of the box. Again, we have SSH tunneling specifically for encapsulating non-secure protocols. So you can actually encapsulate file transfer protocol with SSH. Establish an SSH session first, and then send the FTP information through the tunnel so that you have encrypted default SSH items. So if you look at it from the outside perspective, let's say I'm a network sniffer, like an IDS, I can't see anything by SSH because it's encrypted, which is a good thing as well. Now, there are other mechanisms of securing FTP, which is called a secure FTP, which is SFTP always means SSH. There's FTP /S, that actually means SSL or TLS, which is transport layer security. Both of them have wrapper capabilities and create tunnels, but SSH is a common one for many different applications and is highly reliable and performance based. Now, I'll also talk about RDP or VNC, which are remote desktop protocol types, and they actually send GUI information from one side to the other. You have an RDP server that you can connect to, and in Windows cases, you can actually connect to a Windows box remotely and have a full GUI, unlike SSH, which only supports terminal. The default port here is TCP port 3389, and modern versions operate over TLS, so you don't actually need to wrap an RDP session inside SSH tunneling. This is because SSH servers are not installed by default inside Windows machines. Another supporting administrative protocol is DNS, which helps the internet as a whole. So just like with ARP helping at layers 2 and layers 3, understanding IP address to MAC address, now you can do .coms to IP addresses. So if I go to google.com, is that a routable IP address? And the answer is no. DNS allows hierarchy-based solutions of mappings between domain names and IP addresses. So google.com might go to 8. Right, those 4 octets there. You can have what's called recursive queries, which send queries on behalf of somebody else, or iterative query, which says, I'm going to directly to that server. So when we go to iterative query, saying we go to consco.com, so let's go ahead and get my thing working back. Let's try that one last time. There we go. Let me erase that. All of it gone. Okay, that's most of it gone. Good enough. Let's look at what we got here. Let's look at that pin. Okay. So if I have a DNS client, which is my host, I'm going to do a DNS resolver and say, hey, where's constico.com? It's going to ask the local DNS server. Well, because the local DNS server will only understand your company enterprise.local, they'll forward it on your behalf using a recursive query to either root servers or other servers that are considered authoritative to that name. You don't really need to understand too much about the architectural requirements here unless you dig further into it. Just know that DNS passes queries upwards in a hierarchy-based structure. That hierarchy is based on apex zones, so the start of a zone. So this is a zone. One or more DNS servers may be in charge of conoso.com, and then eventually the answers come back to the resolver client right here, saying, hey, I'm at some sort of IP address. Typically, this operates over UDP port 53, but for cross translation and standards purposes, although you can run DNS on alternative ports, it just wouldn't make a lot of sense in today's world because you're actually utilizing a common DNS service with multiple services that operate on a very standard port. Now you can also do this. You have split lane DNS, which means you have internal DNS servers and you have external DNS servers. These are all outside to the internet, and this is internal. It doesn't look like. We'll just use corporate. Right. That's called split lane DNS or split DNS. So you have a concept of internal DNS resolutions only, and no one touching it from the world. Only DNS responses from other DNS servers around the world are coming back to it. Or perhaps if I have corp.com, if other people from the internet need to understand it, I have DNS servers specifically right here in the DMZ, only for the purposes of resolving corp.com local information or hosted information. Now, there's also a mechanism to use TCP, which needs a reliable connection. You might go, well, why wouldn't we use TCP to begin with? Well, TCP is slower. UDP, you go to many websites at the same time. Think about a web page. If you go to CNN.com, does it not show you ads from other sites? Think about the enrichment. Not everything is hosted at CNN.com, so you might have very fast resolution requirements to load that page quicker. TCP is really for large data returns, and if you need a reliable large data response, such as a host zone. So if this zone had A record, C name, and other details, plot A for IPv6, if I'm returning multiple records, maybe I want to use TCP for that instead. So I mentioned that DNS has hierarchy. Right? Hierarchy is all about, well, I start with the root, which is dot, literally just a dot. Then I have things like .com, .net, .org, which are part of other zones. And ultimately, you might have a DNS server that's only in charge of a very particular zone, such as cloudflare.com, and all the subdomains that go with it. Those zones are based on DNS concepts that have servers attached to each different zone, and that's why you have DNS requests going upward into that stream. External DNSs have charge zones, such as cloudflare.com, google.com, and the root DNS servers keep in charge of understanding and knowing where to go for all these other main .com, .net, .org zones. And they're considered authoritative. So if you're authoritative over cloudflare.com, you might have authoritative servers that NS1, that Cloudflare, and NS2. Right? Those might be authoritative servers only for those, but not for google.com. That's what we mean by authoritative servers. So I talked about record types in our first slide regarding DNS hierarchy and the concept of DNS as a whole. Each DNS zone, right, for cloudflare.com, Amazon, whatever it may be, has different record types. Here's a quick table that helps you demonstrate and understand what these DNS records look like and what they're used for. We have a normal A record, which has simple domain to IPv4 information. We have quad A, which is IPv6, so Amazon.com to an IPv6 address. C names or canonical names are saying, hey, www.amazon.com, blog.amazon.com, whatever. Something needs to resolve to another domain name instead of an IP address. NS record being, here are my authoritative actual DNS servers that say I am in charge of the zone Amazon.com. We have pointer records, also meaning reverse DNS. So remember that pointer records are actually written in reverse as well. So if I say I have Amazon.com and it resolves to 11223344, but I only knew about 11223344, and I needed to know, does that belong to what? Amazon.com? A pointer record would do that. So notice that versus up here, how it's stored versus down here. You have the reversal of 44332211, and we always follow it with a suffix of .n-address.arpa. What is .ARPA? Well, ARPA actually means Advanced Research Project Agency, and it's really kind of a suffix from the olden times of when the networking, the whole concept of networking first started in the late 60s and early 70s. We also have the mail exchange record, which basically says this is where you need to send email coming in and outbound as my email servers. Now, there are many other DNS record types. These are just the main ones that you might see on a day-to-day basis accordingly. So be aware of these as you go forward. Another administrative protocol at layer 7, which can also be deemed as a helper protocol, is DHCP, Dynamic Host Configuration Protocol. You don't configure your own internal IP address statically like 192.168.100.100, right? I don't say that myself. The computer in the network does that for me. So DHCP does that. It operates on UDP ports 67 and 68, and they have different requirements. Like one is a server and one is a client. And it's considered a four-way handshake as well. You request a IP address based on discovery, and then DHCP gives you an offer, and you can also create a DHCP request for a very specific IP address selection. So if you perhaps had a reservation, and how reservations happen, well, it bases it on the MAC address. And I'll say, hey, I need to select this IP address instead for that for my MAC address because you already have a reservation for me. And that reservation says I always get the .100 address to this MAC address here. Okay, everyone else can get .101 to .254 in most cases, and then finally you get a final acknowledgement. So DHCP just basically means automatic configurations of IP addresses assigned to network interfaces. That's all it really means. And again, by default, uses UDP port 67 or 68. All right, it's time for a break. Take a break, pause the video, and let's get back to a demo and figure out how we can actually dissect and what they look like over the network and some administrative commands that can help us out here. I'll wait. Hi, and welcome back. I hope you had a great break. We're going to go and dissect a few of those connections and different protocol behaviors about what we talked about and understand the concept of what happens when you have an open port and a closed port, and also protocol mismatch information. So again, you can have different services operate on different ports, but if you have a client that expects a particular service on a port versus a different one, you might have an issue and you might have different errors. So let's understand what that really looks like. Well, we talked about TCP connections with a three-way handshake. Let's try to generate that. So I have my PowerShell one up. You can actually use terminal command line. I'll be using the mcat package instead to simulate that. So let's go ahead and simulate a TCP connection here. So we'll use Ethernet 2 in my case. I'll have both of them up and running for your purposes. I'm going to capture only on TCP port. Let's pick a good one. Let's pick one that's like 44843, for instance. Actually, let's double check to see anything going to and from TCP port 8443. So we'll use mcat portquiz.net. We'll say very verbose, and then we'll say go to 8443 over TCP. And I'm connected. Why am I connected? Well, I go hello, right? I'm going to get a bad request here because it's operating on a web server because it doesn't understand what hello means. That's considered a client mismatch protocol information here. And interestingly enough, they're hosted inside the European area, EU West internal, which gives me a hint that this might be an Amazon hosted host. But regardless of that, here's my three-way handshake. I'll expand that right here. TCP, and I have a synchronization number. My flags are SYN, followed by a SYN and an ACK together. Right, SYN ACK analysis sequence. There's my flag, SYN ACK, my final ACK, and then I noticed I sent hello in there to add data. So I had hello right here in the next data set, right down here, as you can see, and then followed by enter, and then it gave me a response saying it doesn't know what that means. 400 bad requests. Here's what my item looked like. And that's a great example of, because the web server hosted on it, it didn't understand what I was trying to ask. Let's close it and retry. So I'm gonna control C. And if I control C, look at that. TCP reset instead of a graceful connection handoff. Right? And the ironic part about that is even if you have a reset flag, you don't need an acknowledgement flag, but some clients add the acknowledgement flag in there, which I think is kind of interesting. Let's try that again, and then do get that. And I'm still getting a bad request, even though I'm trying to assimilate the get request. So what we'll do is we'll look up what that means. Let's do a get request manual, manual paste. And we'll make a get web request. Yeah, here we go. And sometimes we need to provide an HTTP version information. So we'll do that. Find that, and we'll say get. And it's saying HTTP 1.1. So HTTP / 1.1. And we're still saying a bad request, because what actually happens is that I'm not actually providing the proper carriage return or other information. And it's basically saying, hey, I don't know what you're saying again and again and again. So control C. And now we see that TCP reset flag right here again. So how do we do that? We need actually a real client versus a raw client. Right? So to do that, I'll invoke something called invoke web request to portquiz.net, which has open ports for us to go testing egress firewall traffic. And I'll invoke a web request. Well, I need to use the URI here. So this is a specific one for PowerShell. And I'll just use HTTP. And I'll put these in quotes. Now I have a response and a 200 OK and here. And here's why. I create the TCP connection, and then I have my application layer information right here. I'll follow the stream, and now I'm getting the actual information here that says get here, followed by the user agent information and host, and keep alive. And it returns to me some interesting, cool stuff here. And we know that the port is open accordingly. And let's see, and we have a closure, graceful closure at the client level versus a reset, the FINAC of the four-way handshake here, or four-way teardown in this case. Final acknowledgement, and then our FINAC. Get back over here. And our last act here. So interesting stuff. So but what about UDP? Can we send stuff to UDP and will we get any kind of similar? Well, let's see. ncat-u, which is for UDP mode, portquiz.net 8443. And I'll send that, not capturing only because I'm capturing on TCP 8443. So let's use UDP. And we'll use -b from verbose. And it's saying to connect it, but I don't see anything here. Hello? But no response. So I'm sending stuff to it, but it doesn't have to respond to me. So I don't know if it actually is open or not. The only way to really understand if it's truly open is if you actually get a response back. So we can use another tool called mmap. And we'll do a UDP scan, and we'll look for different services. And we'll do portquiz.net. And we'll see if it has anything related back in here. So I can actually do that. And it doesn't really know if the host is up or down because it's not providing any information. So I'll make sure we don't have any blocking, pinging going on here. I'm sending a whole bunch of traffic on high ports, and it may not have any information for me. And that's okay because it doesn't need to send anything to me, even if the port is closed. We'll stop that traffic, and then we'll actually just do a check on port 53 for one of Google's public servers, which is 8888. So it's going to come back with some information about that. And then I'm going to close this capture. And while that's trying to look for information, we'll say ending going to host 8888. And it got back something and said generic DNS response server failed, but it did get back an interesting DNS request signature. Otherwise, we wouldn't know if there was a service running on it or not. And this is because it's sending different stimuli, and basically what we see here is a secure DNS certificate information in the response code. So what we'll do is we'll use ncat -u-v -n 888853. So that's still UDP, and we'll say hello. And it didn't give me a response and it's saying, hey, I have malformed DNS potentially because it understands port 53 as a default DNS. Now, it still didn't give me a response, but it gave this one a response stimuli back based on actual DNS inquiries. Well, let's figure out how we can actually do so and how we can actually simulate an actual DNS query request. We'll go back to this guy here, and I'll use NSLookup. I'll say my server is actually 8888 instead of my local DNS resolver. I'm going to say, can you find me, I don't know, xxsystems.com. And then now we have what we have is DNS query information over UDP. Now we finally have our responses locally right here. And we're using the actual client. Notice that it's still giving multiple responses where I have IPv6 and IPv4 addresses on the multi-host name here. And here we go. We have our initial request and responses based on DNS. And look, my destination port is really high because apparently I've been making a lot of connections accordingly. My byte length has changed accordingly too. All right, so that's it for UDP. Another great information. What about if I needed to do SSH, for instance? What does that look like if I were to capture that? We saw everything in clear text so far. Well, what could it hurt? Well, let's close capture right here. Let's look for anything over TCP port 22. Now, first things first, let's make sure that I can actually reach 22 over portquiz.net. So I'll just do that here. Bring this down a little bit, and we'll use. You can also use test net connection, which is kind of interesting. You can use computer name in case you don't have the ncat package. And we can also say portquiz.net, port 22, and then we made a TCP connection, and it gave me a response saying true. And that's the same as using ncat portquiz.net 22, right, for checking for a port. You can say hello, and it gives me a bad address. Remember, this is a web server, so even though the port is open, you do need to speak as if you're a web server. Well, this is great, but isn't 22 related to SSH? And the answer is yes. So first thing I'm going to do is I'm going to try to use my PuTTY client for SSHing quiz.net, say 22, and it's giving me a remote side unexpectedly closed net connection. And that is because, and here we have inactive. So what happened here? Well, we have the SSH client saying, hey, do you speak SSH version 2? I'm coming as a PuTTY client. And then all of a sudden, it closes the connection saying bad request because it doesn't understand SSH. Well, how would an SSH client look like? And we're still seeing stuff in clear text because HTTP is in clear text. We'll reset our capture again. And this time, I'm going to go ahead and create an SSH service from my AWS personal account. Now, you don't need to be doing this. You can just watch me do so. I'm going to create an EC2 instance here. Make sure I keep here. Yep. Launch the instance. We'll create a free tier only one. Don't worry too much about these. I'll just use a default auto assign an IP address just to have a port that is open. Add storage, yes. No, I don't want to add a tag. Let's create a new one, which allows everything inbound, including SSH, unfortunately. That's okay. As long as I have a certificate, public key pair, we should be fine. I'll use that key pair. I already have it, I believe. But let's be sure we do that. Before I do that, so let's look for, make sure I already have that key pair. And I'll need to add that key pair in here. So actually, I need to create a new key pair because I don't have one out. We'll say test demo. It's going to generate that key pair for me, which is really cool. And that's the only time I'll get it. I'll launch the instance. And while that's launching with a public IP address, allowing everything inbound, which is a bad security practice, we'll go ahead and use PuTTyGen. And I'm going to load that private key into my host here. Test demo, yes. We'll convert that to a PBK file, which is test demo PK. I'm going to load that in Pageant. Now, Pageant is cool because it'll load all those keys into nice little memory formats here. So I'll open it up and I'll bring that over here. Add that key, that private key, which is me as a client, into memory. And now I can connect to my instance using that SSH key. Test. All right, here's my public IP address. And because let's capture everything I send to it. Host. Here's my public IP. Let's see if I can ping it. So let's use my command line and just do a ping. You can do so in PowerShell as well. Sending data out, and it's not getting data back in. That's okay. Now let's see if I can connect to it. Instead of launching it, let's try to connect to it. I can connect to it from my web browser, which is great. And there was a problem connecting to the instance, so not sure what happened here. It's running. Let's see if I can connect via SSH instead. And it appears that I don't have that up and running in the mechanism I want. So what I'll go ahead and do is I'm going to terminate that. And then we'll go ahead and try another open SSH service instead. That's okay. I think it's because I'm using a default VPC. And so you'll learn this in a different module or course set. But let's look at a public known SSH. Free public SSH servers, up cloud. This might give some information. free shell account EU. Now you should be careful with some of these. You don't know these are actually up and running. These don't look particularly good to use either. So we can also use something called Shodan. And Shodan will allow you to see who actually has SSH out in the open to the internet that we can possibly use for testing purposes. Now, sometimes this is good and sometimes this is bad. So we'll just use OpenSSH. Sure. And we'll use SSH as for tagging information. And we have some interesting information. So we're going to use SSH. All right, so this IP is open outside in the United Kingdom. So we'll just use that instead. So we'll use this IP host. Okay, so let's use our client. No longer will we need to use my attempted VPC here. And if you're wondering why it didn't work, it was largely because I don't think I put what's called a NAT gateway in there to go ahead and allow egress, internet gateway to allow internet inbound to that. All right, so I'm connected via PuTTY. It's giving me a warning because I don't trust the certificate. And now I can try to log in as testing, and it gives me you don't have an authenticated key to log in as a correct person. Well, there's encrypted packets now, and I don't see anything that says login or key. And I look at there's a Delphi Hellman exchange. If I go to my client information, all stream, it's just garbage here. The key, you might still see some information about the certificate and encryption methods, but you don't see anything related to login. You didn't see me type in the word test in here because it's all encrypted. And the interesting part is that they're using the Raspbian SSH server for OpenSSH. And so that once it creates that tunnel, all encrypted, exchanging those keys, the port is open, but if you're having a troubleshooting connection issue, this is at a higher protocol level, which is authentication as opposed to a network issue. So the port is open on 22. We finally have a port service and client match, but I just didn't have authentication, and for good reason. If you have an SSH server out there, and here's the public key for it, I have to have an adjacent private key to actually access it, usually, and along with a password. So hope you enjoyed this demo. We'll see you in the next lecture and continue further on network engineering and troubleshooting concepts.